We continue our discussion of regression analysis by looking at linear regression. In this lecture, we introduce linear regression for modeling relationships between variables. We remember and we recall that simple linear regression uses one independent variable to predict a dependent variable. And in simple linear regression, it uses what we call the least squares method, which minimizes the residuals. Multiple linear regression is simply an extension of simple linear regression to several predictors. We will come across key concepts that include the coefficient of determination R squared. We will also learn how to interpret regression coefficients and standardized coefficients, and we look at assumptions that underpin linear regression such as linearity, homoscedasticity, normality of residuals, and absence of multicollinearity. We look at significance testing that involves an F-test for the overall model and T-test for individual coefficients. We also look at an example that demonstrates how to predict weight from height, age, and gender. Regression analysis is used to create a model that describes the relationship between a dependent variable and one or more independent variables. And depending on whether there are one or more independent variables, a distinction is made between simple and multiple linear regression analysis. In simple linear regression, the aim is to examine the influence of one independent variable on one dependent variable. In contrast, in multiple linear regression, we look at the influence of several independent variables on one dependent variable. The goal of simple linear regression is to predict the value of a dependent variable based on an independent variable. And so the greater the proportion of the dependent variable's variance that can be explained by the independent variable, the more accurate is the prediction. Visually, relationship between the variables can be shown in a scatter plot. The greater the linear relationship between the dependent and independent variables, the more the data points lie on a straight line. And so if we look at this graphic that tends from low to high, we find that as the linear relationship gets stronger, the data points tend to become more clustered along a straight line. And so the higher the linear relationship, the closer they all are to that straight line. The straight line which best describes the linear relationship between the dependent and the independent variable. This is another way we can think of simple linear regression. To determine this straight line, linear regression uses the method of least squares. What does that mean? Let us look at this graph. It shows a plot of a variable x against observed values of y. However, we have y hat, which is the estimated dependent variable that is given to us by the regression equation. And if you look at this equation, we see y hat equals to bx plus a. So recall the equation of the straight line that we have come across in the past. But the reality is such that we often find that the predicted y, or the estimated dependent variable y hat, often has a different value from the actual observed y for any given value of x. And so therefore there is what we call an error term, and this is what we see displayed graphically here. So for this given value of xi, based on this regression line, we have the estimated value y hat. However, the actual observed value of xi is given to us here by y. The error term, therefore, is the difference between the y hat, which is the estimated value, and the actual observed y, represented on this diagram as this red dot here. And so the difference is the error term, epsilon. And so if we look at this second equation here that says y equals to bx plus a plus epsilon, we see that x is the independent variable, a is the point of intercept on the line on the y-axis, which is here. So this value here represents a, and then epsilon is the error term, and that's it. So if all points were exactly on one straight line, the estimate will be perfect. But this is most certainly not the case. Therefore, we need to find a straight line which is as close as possible to the individual data points. And the goal is to keep the error in the estimation as small as possible, so that the distance between the estimated value and the true value is as small as possible. So in other words, we need to find the line that minimizes the error term. So this distance or error is called the residuals, and we abbreviate it as E or epsilon depending on how we want to put it. So we are looking for that line which minimizes this error term, and this is the principle of linear regression. In linear regression, the method that is used is known as the ordinary least squares. And so when calculating the regression line, an attempt is made to determine the regression coefficients a and b, so that the sum of the squared residuals is minimal. The least squares line, or the estimated regression line, is the line y equals to bx plus a, which minimizes the sum of the squared distances of the sample points from the line. And this is represented on this slide by this equation that we see, which is basically the sum of the squares of the distances of the sample points from the line. The coefficients of the regression line y equals to bx plus a are given by these equations, as we can see on the slide. So b is given to us by this, and a is given to us by this. Again, do not expect you to memorize this, given that you are not statistics majors or students, but it's for us to understand how these come about and where they come from and how we are able to calculate this. The coefficient of determinant r squared indicates how well the regression model predicts or explains the dependent variable. It indicates how large the portion of the variance is that can be explained by the independent variables. The more variance that can be explained, the better the regression model is. And this can be given to us. It's simply the ratio of the variance of the predicted y to the observed y. Multiple linear regression is an extension of simple linear regression that allows more than one independent variable to be considered. The goal is to estimate a variable based on several other variables. The variable to be estimated is called the dependent variable. The variables that are used for the prediction are called the independent variables, or the predictors. And so if we look at the equation for a multiple linear regression, it's kind of similar to the one we saw for simple linear regression. However, it has more terms in it. So we have y hat equals to b1 times x1 plus b2 times x2, and so on to the nth term plus a, which is our intercept. These coefficients are interpreted similarly to the linear regression equation. So if all independent variables are 0, the resulting value is a. If an independent variable changes by 1 unit, the coefficient indicates by how much the dependent variable changes. So if the independent variable xi increases by 1 unit, the dependent variable y is going to increase by bi, and so that's what the coefficient tells us, and that's how we're able to interpret the meaning of the coefficient in linear regression. In order to interpret the results of the regression analysis meaningfully, certain conditions have to be met. The first of which is linearity. There must be a linear relationship between the dependent and the independent variables. So remember when we did the lecture on correlation, one of the assumptions in correlation was that there had to be linearity, and it's the same assumption that we have here for linear regression. In fact, it's even implicit in the name linear regression. Then the second is homoscedasticity. What does this mean? I mean, complicated sounding word, but it just means that the residuals must have a constant variance. Remember, we referred to the errors or the error term as residuals. So these residuals or these error terms must have a constant variance, and then they must be normally distributed. So there is normality of residuals. And then the fourth assumption has to do with there should be no multicollinearity. So what that means, there should not be high correlation between the independent variables. Again, remember this, it tells us about linearity. So this is the first assumption that has to be met. And then for homoscedasticity, we said that the regression model never exactly predicts the dependent variable. There is always an error, but this error must have a constant variance over the predicted range. So if we plotted the dependent variable on the x-axis and we plotted the error on the y-axis, when homoscedasticity is present, the error terms should be evenly scattered over the entire range. So if we look at this graphic here, we see that there is no pattern to it. They are evenly scattered over the range. In contrast to this, which shows a funnel shape, indicating that this variance does not remain constant, but rather as we go further along or the value of y increases, the variance of the error increases here. But we don't want that happening. We want the variance to be constant. The error or the residuals has to be normally distributed. This can be examined graphically using what is known as the QQ plot. Alternatively, we could carry out tests for normality such as the Kolmogorov-Smirnov test or the Shapiro-Wilk test. If we have a p-value that is not significant, it tells us that the data is normally distributed. Multicollinearity means that two or more independent variables are strongly correlated with one another. And this is why we cannot put all the terms of our dummy variables into a regression model, because they are actually strongly correlated with each other. So the problem with multicollinearity is that the effects of each independent variable cannot be clearly separated from one another. A high correlation between the two variables, the two predictor variables, makes it difficult to determine the coefficients for the corresponding variables, and so the regression model becomes unstable. So the variance inflation factor is calculated by this term that we see here. So 1 over 1 minus r squared. And so if the variance inflation factor is greater than 10, that often indicates that there is multicollinearity within the model, and this needs to be taken care of. In carrying out regression modeling, we also need to do significance testing, and significance testing is done on two levels. We want to do significance testing for the whole regression model, so is it a significant model, and then we also want to do significance testing for the regression coefficients. The significant test for the regression model basically looks at the null hypothesis that the r squared in the population is 0. And so to confirm or reject the null hypothesis, an f-test is calculated. And this is how the f-test is calculated. So the numerator degree of freedom is the number of predictors in the regression, and the denominator degree of freedom is given to us by n minus k minus 1, where n is equal to the number of data points. If we take a moment and look at this formula, something becomes apparent to us, that given a certain number of predictors, n, our sample size, influences the F statistic, and in some way it tells us that the power of our sample to be able to avoid a type 1 error is influenced by the number of predictors that we're going to put in the model. So, as a rough rule of thumb, it is suggested that you need at least 10 observations for each number of predictors that you wish to put into your regression model. And so this is a rough rule of thumb for calculating sample sizes for regression models. So at least 10 observations per predictor term that you're going to put in there. The second level of significance testing is for the regression coefficient. So if the overall test is significant, the question now becomes which variables have a significant contribution to the prediction of the dependent variable. We can determine this by checking whether the regression coefficients also differ from 0 in the population, and we do that using a t-test. And the t-test we use a t-test distribution with n minus k minus 1 degrees of freedom, and it's calculated by dividing the regression coefficient with the standard error of that regression coefficient. So our software does this for us automatically. So let us consider this example linear regression model, linear regression. So given weight, height, age and gender, a model is developed to try to predict body weight of a person. And so the linear regression model comes out giving us this result. So we have model that has male, sex, age, height, and then we have the coefficients, and then this is the standardized coefficient. So take a note of this. Where you see the Greek letter beta, it means the standardized regression coefficient, and this is different from the unstandardized regression coefficient, which is simply represented by the letter B. And then we have the standard error, and then we have the t-test, and then we have the levels of significance, whether the p-value is less than 0.05 or not. And so we can see this. So this is typically how we represent a linear regression model. So we have here the R squared is 0.754, okay, for this model, and the standard error of this estimate is 6.587. Now, how do we interpret this table? So if you remember the regression equation, it simply tells us that the predicted weight will be given to us by 47.379, which is the coefficient here, times the variable height, plus 0.297, which is the corresponding coefficient here, times age, plus 8.922 times male. And when we say times male here, we're saying whether the particular observation is male or not male. Of course, not male means female. So, but typically is male or not male. So, or female or not female, depending on how you decide to operationalize it. And then we have the last term, the A term, which is minus 24.41. And you may ask the question, where does the minus come from? It comes from here. So we put in the terms according to their signs. So this is minus 24.41. And so this gives us the predicted weight, accounting for the influence of height, age, and gender. So for the dichotomous variable gender, the coefficient is interpreted as a difference. So a man is going to weigh at least, on average, 8.9 kilograms more than a woman. And so this is really what it is, right? Another way to look at it is also this. For every 1 year increase in age, weight is going to increase by 0.297. So this is also another way of interpreting this coefficient, right? For every 1 meter increase in height, weight is going to increase by 47.3 kilograms. So that's another way of interpreting the model coefficients. Standardized coefficients beta will range between -1 and +1. So you can see here that none of these variables exceeds either extreme of -1 or +1. The greater beta is, the greater is the contribution of each independent variable to explain the dependent variable. And so in this regression analysis, the variable age has the greatest influence on the variable weight. Yes, because look at the standardized coefficient. That of age is the largest. So it tells us that age has a greater or greatest influence on weight in this model.